Hello students, welcome to my channel. Today we will learn one interesting topic, error analysis. Myself Mr. P.S. Chogule from Department of Mechanical Engineering, SITCOE Adra. So let's start how the error comes in picture. So when we calculate something, we come to the approximate answer in case of numerical mathematics methods. And when we find this, which include the number of iterations, our answer, which is approximate, means which is close to the exact solution of an equation. For example, when we take 38.28, suppose at one point of iteration we are going to find out 38.28, then it is 1.3571 likewise. And now we need to take this value in the next iteration, or we need to conclude somewhat, or say we need to conclude over here. Then we are not able to define this point 38.28, 38 divided by 28. So in that case, what we will do, we are simply taking the required digits. Suppose one may take 35714 and one may take it as 1.3571. Now both the answer are approximate answers, not the exact solution. Or for example, the value of pi, which is known to us, which is equal to 22 divided by 7. If you calculate this, it will come it as 3.14285 and so on. But we are always taking it as 3.14. This is the approximate value of pi, and which leads to introduce the concept of error. Means exact solution is somewhat different, and we are taking, or we are concluding the answer with an approximate value, and which means the error is equal to true value, means the exact solution, minus the estimated value, the value which we have extracted. Now let's move forward the roundoff error. Now roundoff error occurs because of computer have limited ability to represent the numbers. As I have told you, pi has infinite digits, 3.14 and so on. But due to the precision limitations, only 16 digits may be stored in MATLAB. Some 10 digits stored in a simple calculator. Likewise, so the omission of such significant figures is called roundoff error. The omission means what? Well, the last required digit is changed based on the value of deleted digits. Means what? I will tell you. We will take this same example, 38 divided by 24. Now suppose we need a 4-digit accuracy. After a decimal point, we need 4 digits. Then we need to look after the 5th digit. If it is equal to or greater than 5, then we need to change the 4th digit by 1, or increase the value of that by 1. And if it is less than 5, then we will keep as it is. We will keep the 4th digit as it is. So here it is. Now same in the case of pi. If I want these 4 digits only while calculating further, then in that case I need to look after the 0.5. Now this location, at this location, whatever the number is, if it is greater than or equal to 5, then we need to add 1 in the 4th digit or the previous digit, and if it is less than 5, then we need to keep as it is the values. Now in this case the fifth digit is equal to 5, that's why we need to change the fourth digit by 1. And such error we called it as round-off error, because we simply round off the digits, that's why we called it as round-off error. Now instead of this, one more term is there, chopping error, which means without looking at that digit when the number is chopped after required digits. Suppose we need to take only 2 or 4 digits, then after that don't consider the remaining terms, simply you need to delete that digit. If you do so, then we called it as chopping error. For example, in this case, if I want this number in this format, means up to 4 digit, then simply chop from 8, you will get this value. So this is the basic difference between chopping error and round-off error. In round-off error, we need to change the digit if it is required, or the based on the deleted value. And in chopping error, we need not to consider the deleted digits. So next one is the truncation error. The truncation error are those that result from using an approximation in place of an exact mathematical procedure. Means what? Suppose if we want to find out e raised to x by using Taylor's series, then it will be like this. Now what we usually do, we usually exclude the terms which can be neglected from our point of view. But as per as the exact solution consider, we need to consider all these terms according to Taylor's series. But what we will do, we will take only the first four values, which leads to the error which we called as a truncation error. Now according to our point of view, e raised to x is equal to these 4 terms, but because of this you may get some different or some approximate value of the function, and that leads to the error which we called truncation error. So in this case only we can say truncation error is equal to the actual value of e raised to x minus whatever we have defined or we have find out the value of e raised to x. Now from this you can memorize that this error can be minimized by increasing the number of arithmetic operations. Now here I need to if I consider e raised to x, this example, then in that case I have taken only the first four values. Now I need to increase these values so that the truncation error will reduce. So in case of any iteration methods or Newton-Raphson method or Newton divide interpolation formulas, we need to define these strips, number of strips we need to define, that is the value of n. Maybe it is in multiple of 2, maybe it is multiple of 3. Now that we need to decide. That ultimately means what? In numerical integration, truncation error can be reduced by increasing number of steps. Means the number n which we need to increase, or we can say as step size, which is nothing but h. We need to increase that step size so that there will be number of arithmetic operations and the truncation error will be reduced. But wait, if I decrease the step size, that ultimately means we need to increase the number of iterations, and while iterating we need to use the previous value in the next iteration, and in the previous value we try to round off the values. That ultimately means if I increase the number of steps, no doubt truncation error will reduce, but at the same time roundoff error will increase. So remember this one. So ultimately you will get one different approximate values which may have a less truncation error but high roundoff error. So based on that we need to find out the optimal solution. So optimal number of strips, optimal number of step size, that we need to define, and by trial and error method we can find out the optimal number of steps. Now the absolute error. Absolute error means the difference between true value and the estimated value. Sometimes we called it as true error also. Second part is of a relative error. Relative error, which is equal to true value minus approximate value, or we can say it as absolute error divided by true value. Or one may represent this in a percentage form, percentage relative error, as a absolute error divided by true value multiplied by 100. So you need to remember these formulas, because sometimes in exam they may ask you about the relative error or the percentage relative error. Next one is the machine epsilon. Is a machine dependent floating point value that provides an upper bound on relative error due to rounding in floating point arithmetic. I will explain this one with one example. What does it mean? The smallest number such that 1 plus machine epsilon should be greater than 1. So for example, if I take this number 1.0695, and in this case the machine epsilon will be 0.0695, or we can simply say it is the difference between 1 and the next nearest number representable as a machine number. So this one is the interesting part, precision and accuracy. So the precision means the closeness of the value with each other. How closely an individual computed or measured values agrees with each other. And the accuracy means how closely a computed or measured value agrees with a true value. Now measured value, if it is agrees the true value, then and then only we can say it as accurate. But when a number of measurements are done, suppose it shows something which is far away from the original value or the true value, then we can say it as precise but not accurate. I will explain this one with one example. Let's have one parabolic curve and one straight line, and now we need to find out the root. So the crossing points, these are the crossing points, and we need to find out by using some numerical methods. And if we find the values which are highlighted over here, now here are the values which you have find out by using any one numerical method, then you can say this as the precise values. They are closely or the values agrees with each other, but they are far away from the true value. So we can say that method is precise but not accurate. But by the other method, if the measured values are in this pattern, then we can say as, because the values are close to the actual value, so we can say it as they are the accuracy. And also we can say it as precise. Actually it is more accurate than the previous one. Or let's explain this with one more example with a bullseye. Now what we call this, is it precise or accurate? Remember that precision words come with the agrees, when the one value agrees with the another one. Now they depend upon each other. Now in this case, this is precise, but they are far away from the true value. That's why we can consider it as low accuracy but high precision. Take the second example. What we call this as? They are not precise, not accurate. Right? Low accuracy and low precision. In this case, it is of high accuracy but in a low precision. The values doesn't agree with each other, but they are very much nearer to the true value. And if it is so, then we can say it as it is high in accuracy as well as high in precision. Next one is the error propagation. As I told you earlier, we are doing the iterations, and at the time of iteration we are using the previous value in the next iteration, and the previous value which is approximate. Why? Because we have made some changes in that, or we made it the round off that, and that's why the error will propagate throughout the calculation. Whenever number of iteration increases, the error will also increase. Now I will explain this with one example. Suppose we need to perform the addition x and y, which we need to find out. X initially we need to suppose extracted from somewhere, and y also extracted from somewhere, which are having the values xx and xy, which are the approximate values, because we have find out this, and the actual values of that is x and y. Now we can say it as x plus y depend upon xx plus yy. How it is? Let's see. So if I put the x plus y, the actual values of x and y at the left side, and the approximate value at the right side, I need to plus this by e. E means the error. Now while summing this, by rearranging the terms, I will get x minus xs plus y minus yy. Now x minus xx means actual value minus approximate value, which is nothing but the error. So ex plus ey is equal to e. So likewise, if I consider x plus y is equal to z, then z will depend upon this error, and now this error will again further propagated somewhere else. So this we called it as error approximation. Thank you, and if you haven't subscribed my channel, please subscribe, like and share.